Good evening. It is Monday night at 8 o'clock, which must mean it is time for some AP stats. We are deep into inference. Last couple of weeks, we've been working on confidence intervals, and the next couple of weeks, we'll be working on hypothesis tests. This week will be z-tests for proportions. And as always, please follow us so that you can get all the updates and latest information. In this stream, we're going to be, like I said, talking about hypothesis tests. We'll start before actually running any test with just a quick lecture on what a hypothesis test is. So how to write HO, HA, null, and alternative hypotheses, what a p-value represents, which is the thing you get at the end of a hypothesis test, what a test statistic is, which leads to a p-value, and also making those conclusions at the end of the test. So kind of start to finish, like, what does this test represent? And then we'll actually run some z-tests. So we'll look specifically at an example of a free response question, similar to one that has come up in the last couple of years, because the free response always, 100% of the time, will have a question that is asking you to run a hypothesis test. We don't know what type of test it will be, but the process of running the test will be consistent from test type to test type, and the conclusions we make will be the same. So over the next few weeks, we'll be practicing running these. But let's just dive into the big picture of what inferential statistics is. Again, you're guaranteed to get a free response question about a hypothesis test, and you're almost guaranteed to get one about the other thing in inference called a confidence interval. And ultimately, all inference is using information from samples to make predictions about a population. So there might be something unknown about a population, like what proportion of all students agree that this course is helpful, or what is the average length of time that people will spend getting to work. And a sample statistic will provide the basis for estimating that thing, even if we're doing comparisons. So we could be testing old treatments versus new treatments, or lots of other examples of comparisons. But ultimately, at the end of the day, hypothesis tests are about p or mu, and we use p hat or x bar to start us off. Okay, and we can do one of two things in inference. We can either make a confidence interval, which we were reviewing over the last couple of weeks, which is when you create a range of guesses for what those unknown parameters might be, or we can run a hypothesis test, which we'll be getting into tonight. And that is when we take a claim about a parameter, which is a null hypothesis. So either I think p is 0.75, or I think mu is 10, or I think the proportion of men is higher than the proportion of women, or whatever the claim is, and then identify what we're investigating, make sure conditions are met, take a sample and do some calculations, and then make some kind of conclusion. We're going to get into the specifics about hypothesis tests. And the first thing we got to do in a hypothesis test, which is one of the easiest things we do in all of AP stats, in my opinion, is we actually write hypotheses. So again, we are trying to figure out something about a population parameter. We're going to use evidence from a sample. But before we even look at a sample, we have to know, what are we being asked about in the first place? And it starts with what is called a null and alternative hypothesis. And the null hypothesis, the label is HO, is always what is claimed, or what would represent no change at all. So if there's a single sample, the null hypothesis will be like p equals 0.5 or mu equals 10. And if there's multiple samples, the null hypothesis is always the p for this sample equals the p for that sample, or the average for this sample is the average for that sample. So the null hypothesis, no matter what, 100% of the time, includes an equal sign, period, end of story. And it's always about p or mu. So p equals 0.80. Perhaps I claim that 80% of students find this beneficial. Or maybe we're running an experiment with treatment A versus treatment B, and we're going to calculate the average difference between the two treatments. Well, the average would be the same in the null hypothesis. We're always starting with no difference, or no change from previous years, or whatever was claimed. The alternative is when we make some other statement about that. So it will involve an inequality symbol. Could be less than, could be greater than. Those are examples of one-sided tests. Or it could be a not equal sign, an example of a two-sided test. Okay. And if it's a one-sample test, you'll always see the same number popping up in HA as you do in HO. And if it's a two-sided test, you'll just see whatever the symbols were. Or two-sample test, excuse me. You'll see the same symbols with a less than, greater than, or equal sign. Okay, multiple choice questions often have, there's like one per test, or they'll just be, what is the hypothesis for this situation? If it's a null they're asking about, always look for equal. If there's alternative, always look for less than, greater than, not equal to, and always make sure that the symbols being used are parameter symbols. So X bar and P hat do not belong in your null or alternative hypotheses. We're always making some kind of decision about an entire population. So we'll use P hat and X bar to help run the test, but not for the hypotheses. So for example, if we see a situation asking us, a recent newspaper article stated 12% of all Americans are left-handed. A student investigated her school to determine if the proportion is the same or if it is different. If you are here live with me now, I see that there are some people here. I haven't seen anything in the chat yet, but if you are here, feel free to take a stab at this. I'm going to wait about 30 seconds before revealing the answer here in terms of what the null hypothesis is. So you don't need to necessarily put HO and HA when you're typing, but put what you would put for your null hypothesis, put what you would put for your alternative hypothesis, and I will reveal the answer, like I said, in about 20 seconds now. Okay. All right, I see an answer from Brandon. His HO, his null hypothesis, is that P equals 0.12, whereas his alternative hypothesis is P not equal to 0.12. Okay. He is in fact correct. Because they didn't specify if we want to see if it's higher or lower, we just say not equals. This is going to end up being a two-sided test. Whereas if the student believed that maybe, hey, more people in her school are left-handed, she would put a greater than sign, or less than, we put a less than sign. But if it's just straight up different, put a not equal sign. Excellent work. Here's another one. Company A claims they pay a higher starting salary on average than their competitor, Company B. They do not release the data to show this, however, so a newspaper takes a random sample of employees at each company to investigate the claim. So based on what the company claims, what would our null and alternative hypothesis be for this newspaper reporter? There are going to be two ways you could write this, both of which are equally valid. I will reveal an answer, like I said, in about 30 seconds. Let's see who's here right now. Okay. I recognize a few names from before. I see Brandon's here. I know I've seen you before, Brandon. Welcome back. Mahfouz, it looks like you're here again. I know this might be all new stuff for you, so definitely try to take stuff in. And Tim, if you're out there, I don't know if we've met yet. Welcome. Definitely feel free to put questions down, try stuff out, see what you think. I'm going to give it about 10 more seconds. Mean of A, mean of B. Yeah, so notice again, we've got equals in our null hypotheses, and we've got that alternative with a not equals or some kind of thing, but specifically greater than in this case. Okay, so Brandon and Jess, your results are the ones on the left. An equally valid version are the ones on the right. Okay, and sometimes you'll see the ones on the right written, because if the averages are equal, then the difference between them will be 0. And sometimes, especially if we're going to make connections to confidence intervals, we actually want an estimate of how different they are. And so we can use the subtraction between them equals 0 to represent the difference. So if you're doing a 2-sample test, you can either put the 2 symbols on either side of an equal sign or not equal sign or greater or less, or you can put both symbols on one side with 0 on the other side. Both of those are equally valid ways to write it. Both of them will receive credit in terms of AP stats. I just wanted to see it both ways in case it comes up in a multiple choice setting. So once you write the null and alternative hypothesis, you're going to run a test. And at the very end of the test, you are going to get what is called a p-value. Okay? And a p-value comes from observing the sample of data, asking ourselves, how likely is this sample to have occurred if the null hypothesis is true? So once we have, say, for example, we believe the proportion of students at this school who are left-handed is 12%, we have to look at the sample of data we actually get and see how likely that was to occur given the null hypothesis being true. So we always believe the null hypothesis at first. We want to give it the benefit of the doubt. We want to trust HO. I want it to be right. I really do. But then we're going to look, how likely is the result I actually get to have happened? Okay, and it's going to be based on the sampling distribution of p hat or x bar. So we're going to start seeing some formulas come into play that you've seen in the past when you were working with sampling distributions or when you were building confidence intervals. Those standard errors, those sigma p hat, sigma x bar, or s p hat, x bar, however you've used it, those are going to start to come into play again in this situation. And a couple of years ago, the question 6 kind of really broke down this process. And sometimes you're asked to interpret the meaning of a p-value. So don't make a conclusion based on it. Actually say, like, what does this p-value represent? So here's a scenario. School district shifting their school day ahead by 1 hour, want to see what the students feel. And the guess is about half the kids will like it, and they want to see if there's evidence that more than half the kids like it. So the null hypothesis, p equals 0.5. Alternative hypothesis is p is greater than 0.5. Take a simple random sample of 300 students, 158 say they agree. So our p hat, 158 over 300 is 0.527. They run the test, and they get about 0.18 for their p-value. We're being asked what this p-value stands for. Not to interpret, or sorry, not to make a conclusion on the test based on the p-value, but to say, like, what does that p-value represent in this context? And I'm going to give you a couple of options here. So does that 0.18, does that represent that there is an 18% chance that more than 50% of students support the shift in school day? Does it represent that if we assume that 50% of the students support the shift, there is an 18% chance of the sample proportion being 0.527 or higher? Or does it represent that assuming that more than 50% of students support the shift in school day, there is an 18% chance of the sample proportion being 0.527 or higher? One of these is the correct interpretation of that 0.18 as a literal p-value. So we want to trust the null hypothesis, and the p-value is going to represent probability. All right, Brandon and Jess, you both think it's B. Okay. What is it about B versus C that makes you distinguish between those two? Because they're really similar. This was a test question. Hey, that's pretty cool. C assumes the alternative. Yep. So if we look back at that definition from the last slide, okay, the p-value, okay, is assuming the null hypothesis is true. We want to trust HO. Okay, and so the p-value is the probability that the observed statistic would take a value as or more extreme than it does. So because our observed statistic in this case was 0.527, the p-value would represent the probability that we would get 0.527 or more if the actual null hypothesis is 0.50. So it is in fact B as in boy. Yep, good memory from your test. I wonder if me and your teacher used the same textbook to get our problems and maybe change some of the things, because this is not, I did not steal this from anywhere. This came from here. I think you just changed numbers. I see. So similar style of question. That's good. That's good. A lot of students initially think that A is what p-values are. The p-values don't represent the probability of the alternative being true or the probability of the null being true. It is the probability of getting our sample result given that the null hypothesis is true. So it's really a conditional probability. So it really, in this case, is the probability of getting p hat greater than 0.527 given that p equals 0.50 in terms of like probability notation. That's what it would look like. I've never seen this come up, but that's what you're calculating. A probability of getting a sample where yours is or greater. So if it's a less than alternative, it's a less than. And if it's a not equal to, it would be, you'd have to double the probability to get the tail on both sides. But it's always given the null hypothesis. All right, Brandon, enjoy. There's some more practice coming up, so go through and watch the replay. Thanks for staying with us for a little bit, and we're going to keep it rolling. So that answer is B as in boy. The place that p-value comes from is called a test statistic. Okay, so test statistic, this is what it looks like. Statistic minus parameter over standard error of statistic. And if we think back to semester 1, that looks really similar to the formula for a z-score. Individual minus mean divided by standard deviation. Instead of looking at individual people, we're now looking at individual sample results from a population. So the parameter, P or mu, should be the center of a sampling distribution. It should be the overall population mean. The statistic is either X bar or P hat, and that standard error on the bottom is going to be familiar formulas from sampling distributions, or we can find them on our formula sheet. I've got the ones at the top left or top right representing the standard error for P hat, given that P is the center of the distribution. Okay, and so it is the thing that leads to us finding the p-value. And you might recognize the normal distribution sketch at the bottom. It is quite literally, okay, a z-score in the case of proportions. So that is a z test statistic because it is a z-score. You have an approximately normal distribution, you can use z-scores. So if we get a z or a t that is really far away from the given null hypothesis, that's our evidence against the null hypothesis that leads us to reject. Okay, and in the case that we just had, okay, p is 0.5, that would be the mean of this distribution. The alternative being p is greater than 0.5. Our p hat of 0.527 is off to the right of that. The question then becomes, how far to the right is that? And what we do is calculate the statistic minus the parameter divided by whatever the standard error is, assuming p would be 0.5. So I would put 0.5 and 300 into the standard error formula at the top right of the page. And I would put 0.527 as the statistic, 0.5 as the parameter, and calculate a z-score. Then the shaded region you see would represent the p-value. So in this case, this is the setup. This is my z test statistic. I put the statistic first, the p hat, minus the p, based on the null hypothesis, and divided by the standard error. So if the null hypothesis is true, our sample result is about one standard error above the mean, a little under one standard error above the mean. Kind of like having an individual with a z-score of 1. Okay, we can then use our probability rules, our normal distribution calculations, normal CDF or whatever you want, to find that shaded region. And that shaded region is the p-value. So before, when I gave you the p-value of 0.18, it's actually about 0.176, which would round to about 0.18. And then now we can make a conclusion about our initial null hypothesis. The null hypothesis said in this case that p would be 0.5, 50%. Our p hat was bigger than 0.5. Was it far enough away from 0.5 for us to reject the idea that 0.5 is really the truth? Not really sure. And if you've already done some hypothesis tests, you know what the punchline is here with this p-value. That p-value of 17.6% represents that if the null hypothesis is true, we got about a 17% chance of seeing this particular sample result happen, which, while not the highest probability in the world, is not low enough for us to start getting suspicious that our sample is really truly an outlier. If we had gotten something like 0.6, 0.7, something that would be more standard errors away from 0.5, that's when I can start calling into question the legitimacy of my sample results compared to the null hypothesis. And that p-value would get lower. So you can picture if the z goes up, that's going to push the shaded region further to the right, lower that probability. And if we have a really low probability there, that's when I can start making conclusions based on this p-value. And so the last thing we have to do after writing our hypotheses, taking a sample and getting our sample results, getting the test statistic that tells us how far away from the null hypothesis we really are, calculating the p-value based on that probability. The last thing we do is decide, does our p-value provide enough evidence to reject the null hypothesis or fail to reject the null hypothesis? So at the end of the day, all we care about is, do I still trust the null hypothesis or do I believe the alternative instead? What I want you to note, if you haven't seen it already, is that you're never going to say accept. We don't accept the null hypothesis. We don't accept the alternative hypothesis. We only have evidence to reject the null or not have evidence to reject the null. And as we know from confidence intervals, sometimes we don't get it right. So it's always possible that even though we say we don't believe the null hypothesis, it might have actually been accurate and our sample result really was crazy. Or the null hypothesis really was true, and we get a result that's so far away that causes us to say, oh, no, there's no way, but it really actually was. So Before you start the test, the comparison is made to what's called a significance level. Okay, the most common is 0.05. The 0.1 and 0.01 are pretty common, and this directly ties to confidence level. So if you've done confidence intervals, you've seen 95%, 90%, 99%. The exact opposite of that will be your significance level. So if you want to be 95% confident, 5% significance level if you're doing a two-sided test. If you're doing a one-sided test, 5% significance level would go with a little bit higher of a confidence. I got to double check this, but this would be for a two-sided test. It's the opposite of the confidence level because confidence intervals go on both sides. Ultimately, 0.05, 0.1, and 0.01 are the most common because 95, 90, and 99 are the most common confidence levels. Okay. So in our case, our p-value is 0.176. If p-value is lower than a significance level, which this one is not, I would say that I reject the null hypothesis. If p is low, reject HO. If p is low, reject HO. Because if p is low, what that says is the probability of the null hypothesis being true based on the results that we get from our sample is very, very low. Our sample data should not exist under that null hypothesis. So either we got crazy unlucky and got an outlier, or the null hypothesis is actually wrong and the alternative is true. And that bell curve should really shift over a little bit to give us some more room. And if that's the case, we have evidence in favor of the alternative. But if in our case, the p-value is greater than a significance level, that doesn't mean that the null hypothesis is right. The alternative might still be right. We just don't have enough to trust it yet. And so we fail to reject the null hypothesis. We're going to say, you know what? This p-value isn't low enough for me to say for sure that my statistic is as uncommon as it could be. And so I will not go with the alternative hypothesis. But they try to trick us. Be careful. Not rejecting the null hypothesis is not the same as accepting the null or rejecting the alternative. Okay, so you'll never reject an alternative. You'll never accept a null. You'll never accept an alternative. You either do or do not reject the null, and either do or don't have evidence for the alternative. Whew. 20 minutes in. Definitely doing a lot. Pause for a second to recap. Ultimately, end of the day, hypothesis test starts with writing null and alternative hypotheses. Figure out what we're being asked about and what we want to gain. What's the alternative? What are we trying to see might be the alternative as opposed to no change or they're equal or p is 0.50 or whatever else. We then take a sample. We've got to check some conditions we'll get to in a minute. Calculate a p-hat or an x-bar. Once we've got our sample, believing the null hypothesis is true, we calculate that test statistic, which is the statistic we get, p-hat or x-bar, minus the parameter was given, p or mu, divided by the standard error based on the null hypothesis being true. That will tell us how far our sample statistic is from where it's supposed to be based on the null hypothesis. And that is going to be either a z or a t. So z statistic is for proportions, t statistic is for mean. And once you've got that appropriate z-score in the case of proportions, you can calculate a probability that you will then compare to your significance level. Okay. If you're running your test in a calculator, all you need to do is write your hypotheses, input your sample data, and then hit enter, and it will spit out the test statistic and the p-value for you to compare to the significance level. And from there, you decide to either reject or not reject the null hypothesis. What's cool about this is because there's 4 things to do, typically we are scored in 4 components on the AP exam, and those are separate spots for us to earn E's, P's, and I's. Sometimes they combine multiple parts together, like they might combine the hypotheses and the conditions together, but typically that last part is its own standalone thing. And so you can really rack up a lot of points on the free response part in terms of hypothesis tests if you get good at the separate components. Okay, so the goal of this first half was to just kind of run through some of the what are hypotheses, null and alternative, what does a p-value stand for, where does it come from in terms of a test statistic, and how do I make some conclusions based on those p-values. And now let's actually get into running some tests. Okay, so just to recap what we need to do, if you're doing this on a free response question, start by writing the hypotheses. Read the scenario, figure out what the null and alternative hypotheses are, okay, and just write them out. Some people encourage you to say what P or mu would stand for. You don't necessarily have to, as long as you have appropriate symbols that come from the question. You then have to, just like anything else in inference, check that the conditions for running inference tests or inference intervals are okay. The easy one to check is that the data comes from a random sample or randomly assigned treatments in an experiment. So you quite literally can just quote in the problem where it says. If you're running a 2-sample test, make sure you also state that they're independent of each other. So it could be a sample of men and a sample of women independently chosen from the same population. Or if we're running an experiment, you'd have to make sure that the treatment and control groups, if you're comparing a treatment and control, were separately randomly assigned to their different groups, and it's not the same group of people doing 2 things. If that's the case, there'll be a different type of test for it. You then need to make sure that the samples are large enough. Just like with confidence intervals, the conditions are the same. Got to have at least 10 successes and 10 failures for z-tests. And if it's a t-test for means, you got to have at least 30 in your sample, or the data you see must already be approximately normal. We're doing z-tests today, so we're looking for at least 10 successes and at least 10 failures. You then got to name what the test is, okay? And the way to name the test is how many samples is it, what letter am I using, and what parameter am I estimating? So 1 sample z-test for a population proportion, or 2 sample t-test for a difference in population means. How many samples? Letter of the test, z or t, parameter that you're trying to estimate. 1 sample z-test for a population proportion. And if it's a 2-sample test, you're probably finding a difference in proportions or looking for a difference in proportions. Your calculators have shorthand versions of these. Please don't write 1 prop z-test when you're doing this. Write out 1 sample z-test for a population proportion. Really do write the whole thing. And then the last thing is to, or not the last thing, the 4th thing is to get a test statistic and calculate a p-value. We're going to do all of that in our calculators for the most part. And once you get those things, you then have to make the decision and interpret what the p-value tells us by comparing it to whatever significance level was given at the start of the problem. If there is no significance level given at the start of the problem, use 0.05 as your standard significance level. And explicitly compare that p-value. So since p-value is less than 0.05, or since p-value is greater than 0.05, we reject or don't reject, fail to reject the null hypothesis, and then either have evidence for or don't have evidence for the alternative. A lot of stuff to do, okay, but we've already practiced null and alternative hypotheses today. We've already talked about what p-values stand for and whether or not we should or shouldn't reject based on what a p-value is. And then the rest is the same kind of stuff that we've been doing with confidence intervals, if you've been with us or if you're there in your class. So with that, if you are still here with me live, hoping that you join in for this, I will reveal answers about every minute or so if you're watching on replay, so you can go ahead and skip ahead. So here's an example of a free response hypothesis test. A pharmaceutical company is testing a new headache remedy. In a double-blind experiment with 100 volunteers, 50 of them are randomly assigned to take the new medicine the next time they get a headache. The other 50 receive the old medicine. 30 people in the treatment group report their headache going away within 1 hour of taking the medicine, compared to 22 people reporting the same thing in the control group. At the significance level of alpha equals 0.05, do the results of the experiment give convincing statistical evidence that the new medicine works better than the old? Probably going to be a single question and just give you a big blank page to work on. And the big flashing red sign for hypothesis test is convincing statistical evidence. If they want you to make a confidence interval, they will tell you construct and interpret a confidence interval. If they want you to run a hypothesis test, they won't ask it directly. They'll ask if the results or if the data or if the sample or if whatever shows convincing statistical evidence. That's code for hypothesis test time. So we got to start with some hypotheses. If you're here live, try to write them out. I'm going to reveal in about 30 seconds. what your hypotheses are. Hypotheses are going to be, what parameters are we trying to figure out here? What are we comparing? I'm comparing something about new medicine versus old medicine. So it sounds like it's two samples. So I'm probably going to need two symbols. The question is proportion or mean, but I don't see anything about averages. I see how many people said it went away in the two different groups. That sounds like proportion. So my null hypothesis is going to be that the new medicine works as well as the old, and the evidence is going to come from the proportion of people cured in 1 hour is the same in each group. The alternative, I should have an HA there, typo on my end, is that the new medicine works better. So the proportion of people who say they're cured with the new medicine is better than the old medicine. New is the treatment group, old is the control group. Wow, just blanked out there for a second. So once we've written the hypotheses, we got to make sure that we can run our test. Do we have to define the P's with specific proportions? Sort of. I think if you use subscripts like this that are clearly connected to the context of the situation, it could be work. I think in an example like this, it could be helpful to specifically name P represents proportion of people in each group who report the headache going away. Especially because the question itself was kind of vague with new medicine works better than old, and we had to define the proportions there. That's probably a good thing. And so we might want to make a little star on the side. P represents proportion of people whose headaches go away within 1 hour. I will say a lot of times when you're writing your description of the p-value at the end, where you say if you reject the null or not, and then evidence for the alternative or not, you're going to write in the context there because you're just going to copy and paste what's in the question. And so even if you don't define it in step one, it will have been defined on your paper at some point. So it should be cool. But Jess, that's a good point. And if you've done this before, your teacher was probably a stickler about it. So short answer, yeah. Longer answer, it depends. And I'm going to keep it moving now. So now we got to check our conditions. Once we know we're doing two sample test for proportions. So we got to see something about these samples. Or we got to see something about these groups rather, because they're actually not samples. They are groups. First condition is it's got to be random. And I see volunteers in here. That's not random, but randomly assigned. Okay, so the two different groups received their assignments randomly. So the participants being randomly assigned to treatment groups, that condition of randomness is met. Okay. If the results end up working, we can't generalize the results beyond these volunteers. We can just say for the people in this group, like the new treatment was better than the old, but because they were volunteers and not randomly selected from a larger population, it might not generalize. But because they're randomly assigned, we can do this hypothesis test. In terms of large enough samples, it's proportion. So the magic number is 10. So look at the number of successes in each group, look at the number of failures in each group. And it turns out in the treatment group, we had 30 out of 50. So 20 didn't work. That's bigger than 10. 22 successes in the control group. So 28 didn't work. So each of those are bigger than 10. All those numbers bigger than 10. And yes, you should explicitly put these are greater than 10. So 30 success greater than 10. 20 failure greater than 10. Some people define it as like NP hat and NQ hat, or NP hat times N1 minus P hat. All of those are fine ways to say it, but you can just write successes, failures, totally fine. Greater than 10, check. Conditions are good. And the test itself, because there are two separate groups and we are working with proportions, this is a two-sample z-test for a difference in population proportions. Now we're ready to type some data in. And what's nice is it'll be really straightforward to just go directly to our calculators. And all we got to do, it took me a second to find the calculator, okay, is when we're running statistical tests, we're going to find the button that says stat. We're going to scroll over to where it says tests, and I'm going to see that choice number 6 says 2 prop z test. It's going to ask me x1, n1, x2, n2. That's successes and failures. So I got 30 successes out of 50 in group 1, 22 successes out of 50 in group 2. And my alternative is along the bottom there. I have a greater than sign. I'm going to calculate my stuff. Just put it right in the calculator, and it'll spit out for me a z and a p and give me my different p hats. So I just have to write them down. Once I've typed the data into my calculator, I can literally say z statistic or z equals 1.6, p-value equals 0.0547. You do not need to show any algebra or anything else. Just type the stuff in and roll with it. But what you do have to do is interpret what this p-value stands for. So we had to compare this p-value to 0.05. And man, is it not close to 0.05, but it is not less than 0.05. So even though a higher proportion of people in the treatment group had their headache go away compared to the proportion of people in the control group, it's not far enough away for us to really be sure that it's actually the medicine doing the difference and not just random chance. So that p-value represents that we've got a little over a 5% chance of getting these 2 sample proportions just randomly if the original population proportions actually are the same. And so because it's not quite low enough, because 0.0547 is greater than 0.05, we did not reject the null hypothesis. We do not have convincing evidence that the new medicine works better than the old, because we do not have convincing evidence that the proportion of people who had their headache go away with the new treatment was greater than the proportion of people who had their headache go away with the old treatment. It's close, but not quite there. If the significance level was 0.1, this would be enough evidence. If the significance level was 0.01, still not enough evidence. 0.05, not close enough. So ultimately, we just did 4 things. We wrote the null and alternative hypotheses. We checked the conditions and took our sample. We named the test and got the z statistic. We got a p-value and compared it to our significance level, deciding to reject or not reject the null hypothesis. And the reason I specifically did a 2 sample z-test is, to be frank, 1 sample z-test for a population proportion are just not that common on the free response. There hasn't been one in almost 15 years. Typically, if we're going to do a z-test, it's going to be a 2 sample z-test. In fact, the one from 2019 was a 2 sample z-test. 1 sample test might come up in like a question 6 situation where you have to then do something else with it. But that's more of a multiple choice situation of interpreting things, and really kind of a like, let's learn how to do this in class. But the actual AP exam is almost always going to be 2 sample tests, a comparison of treatments or a comparison of different groups from a population for the most part. So definitely get used to those. And ultimately, that was a good, well-practiced thing there. We still got some time in the stream. Some further topics for hypothesis tests. We're going to do some t-tests next week. We're going to do chi-squared tests the week after that. But some other general topics that you should make sure that you find out about in your class that we can cover in another stream, or I can stay and answer some questions about now, is they might ask you about errors. Like that conclusion we made, like the proportion of people might actually really be higher for the new medicine than the old if we had had a better sample or we had like done it again. So it's possible that we got it wrong. And there's what's called a type 1 error versus a type 2 error. And we could have just made a type 2 error because we failed to reject the null hypothesis. Maybe we failed to reject the null hypothesis when we should have. That's a type 2 error. If we had rejected the null hypothesis, there's a chance of us making what's called a type 1 error, which is us rejecting the null hypothesis when we really shouldn't have. Oops, we did too much. So type 1 is like we overdo it. We reject when we shouldn't. Type 2 is we didn't do enough. We did not reject when we should have. So in that case, a follow-up might have been, what type of error could you have just made? Type 2, because we failed to reject. And then the other thing is what's called a power of a test. This is going to be a separate lesson for us in terms of 5 streams, but it's the chance of getting it right, like the chance of correctly rejecting a null hypothesis when we really should have. And so with that, it is officially 8:40, so I'm on the clock for a little while longer if you guys are still here live. I can make up another problem for us to do that we could try together. I can go over any specific part of this. I know there's kind of a lot to take in all at once. Jess, it seems like this is something you've done before, so I'm hoping that was a good review for you. If you want me to make up another question for you to try, we can do that. If not, any other questions that you have, kind of leave them in here. Otherwise, we will wrap it up once you guys feel like you've gotten what you need. We do have some time, so I can definitely take other questions or make up some other problems. How many tests total? Yep. In terms of like how many types of hypothesis tests, so you should be able to do one sample z-test. You should be able to do a two sample z-test. You should be able to do a one sample t-test. Two sample t-test. You should be able to do a matched pairs t-test, which is kind of like the two sample test, but you actually only use one set of data for it. Those three, the three t-tests are what we'll talk about next week. And then there are two main types of chi-squared tests you have to be able to do. So there's what's called chi-squared test for a goodness of fit, and a chi-squared test for independence. And I guess there's technically one called homogeneity, but I haven't seen them ask that on an AP exam actually ever. So chi-square test for independence is the most likely one for that. So we just did a two sample z-test. The t-tests are all going to be ones we look at next, like specifically in next week's stream. And the chi-squared tests are going to be a few weeks from now. Chi-squared test is specifically for like lots of categorical data. So if you have like age groups, genders, or opinions, or, you know, we asked 3 different age groups their opinion on these 3 topics. And you have a bunch of yeses and nos and percentages and stuff. That's going to be a chi-squared test, where you're trying to see if there's an association between those categorical variables, if you can't make a scatter plot out of it because they're not quantitative. If you're talking about means, t-test. If they're talking about proportions, z-tests. Those are the only ones I know. Sometimes people do tests for slope, but I've had it pretty much confirmed for me by some AP readers that they're not going to put slope tests on an AP exam because it's just a more obscure thing. The big ones are z-tests and t-tests. My prediction, Jess, not that you asked for it, is that this year will be a chi-squared test. 2019 was a 2 sample z-test. 2018 was a 2 sample t-test. 2017 and 16 were both chi-squared tests, so we might be due for a chi-squared test or possibly a matched pairs t-test in terms of the free response question. Multiple choice, you can get any of them. Never know. Yeah, so the predictability is in question. So there's 6 free response questions. In question 1 through 5, you are 100% guaranteed to have one of them of the 5 be a hypothesis test. End of story. It will be, is there convincing statistical evidence that something, the new treatment works better than the old treatment, or the average recovery time is lower, or, you know, the proportion is not 12, or whatever, you know, whatever it is. That is guaranteed as one of the 1 through 5 questions. Question number 6, like where they start to do the more exploratory thing, it can always have some elements of hypothesis test in it. And another thing that's fairly common is you'll have in 1 through 5, you'll have your single question of a hypothesis test. And then maybe in another question, like part C is asking like, are the conditions for this test met? Or there's 2 histograms and part A was describing the difference between them. So you like did your center shape spread, you compared them. And then part B would be like, they run a 2 sample t-test and they get this p-value. What should they decide? Where you might be asked like a little component of this as opposed to running the whole test. But one of the free response questions will be running a test from start to finish, hypotheses, conditions, name it, test statistic, p-value, conclusion, reject, not reject. Guaranteed. Other thoughts, questions, feelings? The other way you can tell most of the time that your free response question is the hypothesis test question is it won't have like a part A, B, C, D. It'll just be a single paragraph with a single question. And that's the like, oh, they're going to score me. They're still going to score you on multiple components, but they don't separate them into separate questions. So if you do see just like one question on a blank page, probably got to run a hypothesis test. And it'll maybe have a part A, part B. Test on all the tests. Oh, there's always the test on all the tests. Yep. Good. So I hope this was like a good general review for what you needed to do. If you got a test next week, come back on Monday so we can review the t-tests. And then we'll do chi-squared here in a couple of weeks. And the other plug is at the end of March. Fiveable is going to be offering, they call it Cram Pass. I'm not sure exactly what the cost is, but you basically pay like a one-time, like all these streams are free, all the replays are free, everything else. But if you get the Cram Pass, starting at the end of March, you'll have access to like another exclusive stream once per week, as well as like practice questions that get published for those streams created by us just at Fiveable to be representative of AP questions as like extra practice to do on top of the stuff that you're doing. So be on the lookout for emails about that. But I'll still be here Mondays at 8 for our free streams, reviewing stuff. Just listed a date and time. Okay. That is so like at the end of the day, like I'm getting paid for this. Like I'm a teacher, but this is kind of my little side thing where I can come on here and do streams for people. So they're, got to pay the bill somehow. There's going to be, so the passes I don't know how much they're charging for it, but that will be a thing. So just be aware. It's not going to be cost prohibitive. Like it's not going to be nearly, it's not going to be like, I think it might be the equivalent of like buying a review book. You just get a live person to interact with. And in fact, it'll be this guy. So if you've enjoyed my fabulous demeanor and my wonderful examples, then I've done AP readings. Like I kind of know how things can go here and there. So definitely think about it, but keep enjoying the free streams in the meantime. And there will be more of those even when the cram passes are in session. So I think with that, everyone, thanks for stopping by, and I'll see you next time. Take care.